And then I directly continue with the next presentation. I hope that I'm more or less halfway with the time. But so now I continue with the Dynaville project. Also here we cooperate with several partners, and their logos are depicted here. So again, we have knowledge institutes, we have a technology provider, logistical water treatment, Daamen, which he did already some experiments himself and cooperates with Logisticon. And we have again Waternet and the waterboard Brabantse Delta that cooperate together in this Dynaville project. The Dynaville project comprises several aspects. We look to two-stage wastewater treatment systems, and then especially this first high-loaded A stage is interesting for our research, because there you can get conversion of soluble organics into colloidal matter, and you can collect this colloidal matter now in a settling tank, but maybe with a new innovation you can collect it also with dynamic filtration, which I will explain after this. And mainly at TU Delft there's a PhD student working on anaerobic digestion together with dynamic filtration. So if you collect organics from sewage, then you also want to send them, for example, to the digester. So that's a nice collaboration. Now there's a bit a repetition of what I showed before, but you can collect the organics in different ways by applying different techniques. And like I said, in this high-loaded first stage, you can convert dissolved organics from the wastewater stream in suspended material, and then you get more organics in a very short stage, because the hydraulic retention time is very short. And after that, you also have to invest less energy so less aeration for getting rid of these organics. Some advantages and disadvantages of the different technologies that we also investigate. So, for example, fine sieving of influent seems promising, but then you miss the dissolved organics, which is still a substantial fraction of the sewage. You have existing two-stage treatment systems, the so-called AB systems. I will show more, but they have two settling tanks, one intermediate and one in the end. So a bit larger footprint, which could be sometimes a limitation. And what also is visible, that we don't actually know the optimal conditions in this first A stage. So that's also what we investigate in this research. We already heard this morning about MBR systems. They have small footprint. But fouling and the energy demand can be a limitation or a drawback. And then we are now investigating dynamic filtration, where you also have a small footprint, but hopefully a lower energy demand, but sometimes also a drawback and lower effluent quality. So if you want to reuse it for high purposes, high quality purposes, then maybe you need to apply another technology as well. But if you discharge it, or if you want to use it for irrigation, it could be already very interesting. What we investigate in the research is the control of the dynamic membrane, so dynamic filtration, dynamic membrane. And there you want to have a high flux and good effluent quality, but that's something you can play with, and that's what we are doing actually in our research. Yeah, more or less said is you want an optimal A stage, maximum amount of suspended organics to collect them. With dynamic filtration in an activated sludge system and settling tank, compared to that, you have a shorter sludge residence time if you collect the organics with dynamic filtration, and of course a smaller footprint. And in anaerobic dynamic membrane bioreactors, you can separate the hydraulic retention time from the sludge retention time. So you have a higher sludge residence time, so more time for conversion of these organics to biogas, and also a smaller footprint. This is how it looks schematically. We are working on the blue blocks, you could say, so optimal conditions of the first high-loaded stage. We apply dynamic filtration of this A-stage sludge, and we also investigate dynamic filtration of normal or low-loaded activated sludge systems. And we also already this whole concept could be very interesting if also the cold anemox will work. There are now also pilot experiments in the Netherlands, and with cold anemox you can have the nitrogen removal from the sewage without a lot of energy, and also without a need of organics. So that would facilitate the possibility to collect as many organics as possible in this first stage. So if you collect these organics, then you can send them to the anaerobic digester, also within the dynamic filtration membrane, and convert as much as possible of these organics to biogas. And in this whole concept, then you also have the possibility to collect nutrients, but we don't look to this we don't investigate this in this project. So process conditions in the A stage, they are not yet fully understood or fully known. So we are working on an inventory of existing two-stage systems, and focusing on the first stage, of course, and search in literature. We do some tests. We're also going to test in full-scale systems what happens with organics and also with nutrients, and how processes take place and how we can optimize these processes. And we are planning to make a pilot here or I don't know in Amsterdam, but close to Amsterdam, because we are doing that together with Waternet. And all of this is to increase the knowledge of the process aspects that are important for a maximum COD organics collection. This is an example of some wastewater treatment systems. Actually in the Netherlands we have only 4, I depicted here 3, but 4 two-stage systems that are working with a high-loaded A stage, have then an intermediate settler, and a low-loaded second B stage. These values here are from the A stage. So what you see is that there is a high sludge load in these systems, and that the retention times are very low. So what you would like to have is that you have high organics removal already in this stage. So they in general have quite high organics removal, but you also see differences, and we try now to find out what are the tricks to have the highest removal of organics. So at least it's really necessary to have a high loaded system and a short residence time. But we still hope to learn more from the data. We are still getting data also from foreign wastewater treatment systems, so from other countries where they apply high-loaded wastewater treatment systems. What you can also see from these numbers is that the effluent from the A stage, so the water stream, the sewage that passed the first stage and the first settler, still contains quite a lot of suspended solids. And that's why it's interesting to investigate also dynamic filtration, because you could try to collect these suspended solids, and that could be possible with dynamic filtration. Dynamic filtration is actually more or less similar to membrane filtration. I would almost say conventional membrane filtration. Only difference is that you don't use a membrane, but a support layer which is of a cheap material, also less dense than a membrane, because in both systems, on the membrane bioreactor, but also with this carrier material, you get very quickly a natural cake layer, because sludge contains all kinds of microorganisms and other organics, and this natural cake layer is eventually responsible for the filtration. And what we try to do in our research is to control, of course, this natural cake layer, because that's the big trick, of course. But it's easier to have, for example, a backwash, because the support layer is less dense than a conventional membrane in a membrane bioreactor. So here are some of these characteristics. So the dynamic support layer is of a relatively cheap material, and pore sizes can vary from a few micrometers to half a millimeter. On this support material you get a natural cake layer. That's why they also call this technology sometimes secondary membrane filtration or self-forming dynamic membranes. And like I said, the cake layer that's formed is ultimately responsible for the filtration, and therefore dynamic filtration could be an alternative for settling tanks or for the membrane bioreactors. We did a literature review with STOA, the Dutch organization that combines research from the water boards. There's not yet a lot of literature on dynamic filtration, and most of the research that's done is done in relatively small lab scale experiments. We have seen papers of 2 upscalings, and these results look promising actually. Most research is about submerged systems, because that's a bit more energetically friendly, and gives also less biomass stress, because with a dynamic membrane it's nice if you have nice flocks with a bit open structure, so you form a natural natural pores. And of course, if you read literature, not all the details are very well described very often. But we also saw some important aspects like sludge morphology. Like I said, filaments are then not a problem, which are normally a problem in settling tanks. The sludge load high is an advantage according to the literature, so that could fit very well with our A-stage high-loaded systems, and a low sludge age as well. And the pH might have an influence, but very often that's a bit difficult to control in municipal wastewater treatment systems. Also, a lot of support materials are used, so you have non-woven materials. We use actually woven materials in our experiments, and we use polypropylene, but in literature they have used a wide variety of different support materials. And mainly activated sludge systems are used for dynamic filtration, but also MBR and even surface water can be filtered with dynamic filtration. These numbers are also from literature. You also see quite some variation, but fluxes of 50 liter per square meter of dynamic membrane per hour is possible, and also the effluent quality can be very high, and very often even below the detection limit, which is very often set at 5 milligrams suspended solids per liter, which is comparable to a clarifier, or even sand filtration could be comparable to this. So that's very promising, so that's why we also continued with this research. We have some small scale tests, but with real sewage. And if these are, we have different sizes, and if these are successful, we will continue with a bigger pilot test. We will investigate A-stage sludge filtration and the B-stage sludge filtration, and then hopefully also understand the parameters to control the flux, and that's actually controlling the dynamic membrane. Here are some results of dynamic filtration of activated sludge. So we used a relatively small unit, and we had some short runs. What you see that if you start with a clean support carrier, first the flux is very high, but you also see that in like 2 minutes you have a cake layer formed, and the flux goes down. And then, of course, the effluent quality also is improving. And these fluxes of activated sludge with this small unit are actually very interesting if you compare them to conventional membrane bioreactors. We also did that on A-stage sludge, where you see more or less the same pattern. And what we do is then after half an hour we give a backwash, and this backwash is here in these runs quite effective because you repeat more or less the same curves. Then we made a bit bigger module. It looks like this. It has 0.9 square meter filter surface, and we also have like 3 filters next to each other. They are then in a sludge container with aeration. We have the possibility to have the aeration under the module to have some air scour. Filtration is from outside inside. Then the filtrate goes to the top compartment, and then you have here the level difference between the sludge outside and the filtrate in the top compartment, and that's the driving force of the process. And we use quite small hydrostatic pressure in this way, or so that's interesting. Here are some results of filtration of A-stage sludge continuously, and what you see here is that these fluxes are now lower, so we are still, this is quite recent result. We're still investigating why it's now a bit lower than what we saw with our smaller unit. But what we also saw in these experiments that at least the filtrate, so the effluent quality is very high. And it's normally below the detection limit of 5 milligrams suspended solids per liter. This research is conducted in the TU Delft by a PhD student, and there the feasibility of dynamic membranes for sewage sludge treatment, digestion is investigated, and that's a little bit more fundamental. So also the formation of the dynamic membrane and how this worked in a fundamental way is investigated, and that complements our research hopefully quite a lot. They will apply lab scale bioreactors and submerged in a side stream. So this research now just started, and we are working on a scientific literature review. So together with the STOA study we conducted, and at the TU Delft, where also then some literature review is done by the PhD student, of course, and also especially focused on wastewater treatment or anaerobic wastewater treatment for their research. So I sum up my 2 presentations, which were actually focused on new concepts for the to gain the resources from wastewater, because wastewater contains water, energy, nutrients, and I gave 2 examples of projects that we conduct that are working on gaining these resources. In the sewer mining project, we investigate combination of technologies. I focus on forward osmosis, but we have more technologies in this project. Forward osmosis membranes are showing low fouling, and it's still reversible, so that's interesting. And the developments could lead to, in the end, if it's applied to high quality water, and hopefully in an energy friendly way, especially if you can combine it with concentration of sewage and then digestion of this sewage. The forward osmosis performance depends on a lot of aspects, and also the developments of the forward osmosis membranes are still going on. So hopefully they can also make steps, and hopefully at a certain time the production could be commercially interesting, so then also the costs will go down, because now it's still not really feasible to apply this in practice because of the costs. Then in the Dynaville project, it's also aimed at collecting energy, organics from sewage, which then leads in the end to less aeration energy that's needed for the wastewater treatment, and also hopefully less energy use, so that's a win-win situation. And there is a possibility for nutrients recovery. So with that, I want to thank you for your attention.
Thank you very much, Kees.